All right, thanks. My appreciation to the three S's for inviting me here, and it's a pleasure. And looking at my abstract, I realized that I was over generous with what I promised to do, so I'll have to limit the topics up to 30 minutes. And so before I forget it, here is a number of people that have collaborated in this, and I'd like to recently with Agapi Emanuelidou, some of you know at UCL London we have been doing some new things. And for those of you that are familiar with the strong field community, I want to emphasize that this is George Nikolopoulos and not Lambros Nikolopoulos, who is in Dublin. I happen to have two ex-students and two collaborators, Nikolopoulos. Then let's now, if you submit any system, any bound system to strong radiation, you will have ionization, and depending on the pulse duration and the intensity and so on, you will have multiple ionization. Now this has been known for 40 years or more. Now a question that arose from the very beginning and was explored was whether the electrons that come out of a bound system, they come out one at a time, in other words, in a succession of ions. The neutral goes to ion, the ion to double ion, and so on, or whether there is a possibility or a process by which several electrons go out together. And the most elementary process of that is what Steve mentioned in helium, where we have single photon double ionization of helium. So this is what this will be the focus of my talk. Now, for photon energies up to say 300 eV, the process begins with some subvalence electrons, not the valence. Optical and infrared lasers, you just peel the system from the outer electrons, one after the infrared and optical don't see the inner electrons, no matter what the intensity is, until you have removed several of them. Now, for this range, now you start from an inner subshell. Say in xenon, you start from the 4D, in Creton from the 3D. And these are some single photon processes, but they're very quickly few photon processes come into play, 2, 3, 4, 5, etc. In contrast, if you have a few keV, 3, 4 keV, you start pulling electrons from the deep shells, and the process is dominated by single photon processes, a sequence, of course, a cascade of Auger and so on. So these are. There is no sharp demarcation line between the two, but for my discussion, this will stick to that. So I will be talking about that range. Now, a pictorial representation of sequential versus direct, which I will come back to. Take the neon atom and take, in fact, specifically, I will discuss what happens to the neon atom at 90 eV photons. So this is the sequential, neon to neon plus to neon double plus, etc., etc. Now, there is a possibility of a direct process, and this is what I want to discuss. There is a possibility that two photons eject 2 electrons from the neutral, 3 electrons and take you to neon 3 plus, 4, etc. 6 electrons absorbed together, simultaneously, whatever word you want to use, from the 2p6 shell will lift all 2p electrons. And so what I want to discuss is what is this possibility, okay? And what are the relevant cross-sections and what can we expect. So we'll come back to that because we'll look at this a bit more. Now these issues, as I said, arose a long time ago. It first came up in '85 when the lasers were picoseconds and the photon energies were a few eV, at most 6 eV. But then it surfaced again 25 years later, in 2009, under radiation by flash. Then, in those days, people saw up to krypton 6 plus, 7 plus, so multiple ionization. Now here it was up to xenon 21 plus. The photons were bigger, the photons were about 90 eV. And now this was the situation then in 85. In xenon, let's say, with 6 eV photons. Here are the sequential, and here are the direct. And now here is the situation in 209, xenon with about 90 eV photons, which means you start pulling out a 4D electron. It's a single photon process, Auger, which leads to xenon double plus and xenon plus. And then very quickly it becomes a few photon process. And what looked mysterious at the time was that up to xenon 21 plus was observed. Now, if you look at the energetics and so on, if you look at this sequential issue, you find that the highest order of nonlinearity is about 7. So you start with single photon processes, 2 photon processes, 3 photon processes, up to 7 photon processes. Not really very high order. Okay? And of course, this was debated a lot because was it sequential or was there something else happening that all 20 electrons somehow went out, or 10 electrons from the 4D shell. And if you read some of the papers that were written, there has been quite a bit of speculation. Now, I bring this up because it's, in xenon in particular, the issue was complicated in some people's mind anyway, because xenon, if you ionize the 4D electron with about a photon of about 100 eV, there is something that is known as a giant resonance. Well, I never understood what is giant. It's about 1 order of magnitude bigger than the other cross-sections, but nevertheless, there is a resonance there, and some people call it collective resonance. Okay. And so there is a relative larger cross-section, and this, by the way, is even a single particle effect. I mean, you can get it. It's due mainly to the D to F transition, which is a double well, and so this is. But nevertheless, this is a very sophisticated calculation. You have to use a sophisticated way of calculating the correlation now in this for the shell, and this has been done with a RPA. So that's just a sideline of the. Now, so this was the background, if you want, of what the story is. Now let me summarize for you the situation. Now, when we have optical or infrared radiation, then, as I said, the radiation peels electrons from the outer shell. And a nice picture is that the potential that the electron sees is bent back and forth. And then every time it's bent, the electron can either tunnel out or even go over the barrier. The intensity has to be large so that this barrier will bend sufficiently. And if it is, the frequency is infrared or optical, this means that this is slow. So therefore the electron has time to tunnel out. If you do the same thing with an X-ray at the same intensity, you can bend this barrier the same amount, but it doesn't stay bent that much because the period is short. So it doesn't have as much time to tunnel out. So therefore, the dominant picture here is tunneling, and then there is something called recollision. Recollision means that the electron that is pulled out, those of you that are familiar with the strong field physics, you know, but recollision means that the electron is pulled out, is set into oscillation by the field, and then the ponderomotive energy, which is the energy of a free electron in a field, the kinetic energy, this can bring the electron back, which can knock out another electron. And that's the only mechanism by which, in infrared and optical, 2 or more electrons can be knocked out. It's called recollision. And for this, the ponderomotive energy must be bigger than the binding energy. And of course, if you have infrared and so on. Now, if you now go into the short wavelength, X-rays, XFEL, XUV, etc., then this picture doesn't apply. You start pulling electrons from inner subshells or inner shells. Then we go to what's called multi-photon absorption. Now, intensity. People tend to say, oh, 10 to the 14 watts per square centimeter, 10 to the 15 watts per square centimeter. That's large intensity. Yes, it is large intensity for infrared. It's huge. But it's not large intensity for a XUV or a soft X-ray or an X-ray. Here is now the criterion. Here is the ponderomotive energy. Here is the photon energy. 1 eV, if you have 10 to the 13 watts per square centimeter, then the ponderomotive energy is about equal to the photon energy. And this now is more than that. And to have the ponderomotive energy 1 eV, you need about 10 to the 12. But now if you take 100 eV photons, that's what I will be mostly talking about in this range, 100 eV photons, and you take 10 to the 13 watts per square centimeter, the ponderomotive energy is 6 orders of magnitude smaller than the photon energy. So there is no ponderomotive energy significant. And you would need, at 100 eV, you would need 10 to the 19 watts per square centimeter for the ponderomotive energy to become comparable to the photon energy. When the FELs and the XFELs, etc., can master that intensity, then it will be a somewhat different game. And of course, it's advertised that it will happen one day, but now, all right, now, ionization now, and multi-photon ionization under those conditions. There is no recollision, there's no. So the ponderomotive energy, which scales in proportion to the intensity and inversely proportional to the square of the frequency, is much smaller than the photon frequency. Now, in single photon ionization, the transition probability is a cross-section times the photon flux. I put the intensity here, but it's the photon flux, right? In an n-photon ionization rate, this is nonlinear. It depends on the nth power of the intensity. This is a cross-section-like object, which is a generalized cross-section. This is centimeter square for single photon. This is centimeter fourth second for 2 photon, etc., etc. Okay, now, so therefore, this is a nonlinear process to start with. And I say to start with, you will see why I emphasize that. So now, under these conditions, if you have a process in which you simply observe, say, 10 photon ionization of some species, and you plot the log of the yield versus the log of the intensity, you should see a slope of power n because of that power. If that slope is not n, something else is happening, and you have. Now, those of you that may be familiar with the Keldysh parameter and prefer that, though I don't prefer it, the Keldysh parameter is, when the Keldysh parameter is larger than 1, then with that we are in this regime I'm talking about. The Keldysh parameter in the infrared strong field physics is smaller than 1. Now, here is an elementary problem, a generalization of what Steve talked about. This is 2-photon double ionization of helium. If you want, it's the most elementary 2-photon double core hole process there is. Now, this problem was launched sort of as an academic exercise. So here is where you take about 45, 50 eV photons, you ionize helium, then the ion can also be ionized by 2 photons or 1 photon, depending on whether it's 45 or 55 eV. But then there is a possibility, a probability, a transition amplitude, that 2 photons take out 2 electrons. So this is double, 2-photon double ionization. And we will be generalizing this pretty soon now, okay? So as I said, this was launched as an academic exercise in these two papers. Now, I had assumed that Johannes Feist would talk about this because he has done excellent work on this problem, but I will not talk about this. But this is just to show this elementary process. Okay. Now, what is the next thing? Lithium. You have 3 electrons. So we could talk about 3-photon triple ionization of lithium. So what do we need for that? Well, here is lithium. This is a system that has been studied a lot. If you go up there, there are the so-called hollow states. Lithium is 1s squared 2s. So if you pull out 1s electron, then you have a hole in the 1s. This is called the hollow atom. And then you have there these funny states which can decay to lithium double plus, to lithium plus. So this is a well-studied topic. Now, then, if we have photons about 75 to 80 eV, you can, energetically, you can have 3-photon triple ionization of lithium. So this is that old diagram. See, I have taken only part of it here now. And so about 80 eV, 3 photons can take out 3 electrons. Now, an interesting question, of course, here also in helium was that how do these electrons go out? They are angular. There are 2 issues here. One is what's the cross-section? What's the probability of seeing that thing? Because what else is going to happen? First of all, you are going to ionize helium and lithium and lithium plus and lithium. Then this is the sequential things that I said, okay? Then you will ionize this. So these are the sequential. And usually these are the stronger channels. So they mask the direct things. So then we will see, because I will talk about something more ambitious than this. So, but this is a problem that I think its time has come. And with Agapi Emanuelidou, we have been looking at this and some very, very rough things. But I mention this because Emanuelidou, for the last few years, has done some very nice work on triple ionization of lithium, launching an 1s electron and then doing semi-classical calculations. Now, I know some people frown on that. I say classical, semi-classical. I did too some time ago, but I have been convinced by the results. And so the litmus test of these things is the angular distribution of the electrons. And she has managed to get some very nice result of, so this is not multiphoton, but I mentioned this to show that. So now, in this energy range, should be possible to get 3-photon triple ionization of lithium plus all the sequential processes. Why not something more ambitious, like 6-photon, 6-electron ejection in neon? If you have 90 eV photons, and people do have, and now you can take the periodic table and go down, of course, but 18 electrons from xenon. I will not discuss that. But let's discuss neon a little bit, because it's not as much as you think science fiction. Okay? I hope to at least to reach. Now, this sequential process is multiphoton cross-sections. You need multiphoton cross-sections. 2, 3, 4, 5, 6. Okay, a multiphoton cross-section is an object like that. Instead of one matrix element, you have a summation of intermediate states, and you have to put a basis set here and so on. If you have never seen that, just I cannot explain this in detail, but it's to calculate a multiphoton cross-section, to calculate a single photon cross-section, you need an initial state and a final state. You take the matrix element. To calculate a 2-photon cross-section, or more than that, you need the whole spectrum of the atom. All right? You need a basis, as good a basis, and then a good computer, and then good luck. You get a number. Oh, and now, these things have been calculated, by the way. Hydrogen, of course, the workforce. Now, the hydrogen, there are calculations in hydrogen up to 16-photon ionization. These were done by Edna Karule in Latvia in the 70s. And these are benchmark calculations. This is a 6-photon ionization cross-section of hydrogen. It's a real thing. Okay? Now, I don't think that these have been published. I have a report that she sent me, which is in Russian, but I can look at the figures. And I have had it for 30 years or so. And
power of minus 88?
Pardon?
It's 10 to the power of minus 88?
Well, this number is so large because she has scaled it. A 6-photon cross-section is 6 times 30 is in centimeters seconds is 10 to the minus 180. Yeah, but. The flux you are going to use is 10 to the 30 photons per square centimeter per second. 10 to the 30 to the 6th power is 280. So 10 to the 180 times 10 to the 100 minus 180 is 1. So relax. So no. Okay. All right, now, as I said, there are calculations in hydrogen, and experiments are not done in hydrogen, but there are ways that to scale it. But here are some numbers. All right, 7-photon cross-section is 10 to the minus 203. Right, but you know now why this is not ridiculous, because the flux is ridiculous. So, okay, here is neon now. So here now we're going to do this, the real thing now. Neon and 90 eV photons. And we are going to write a set of equations, so differential equations. Now, you will take my word, or we'll assume that we can get those cross-sections somehow. Okay? There is a procedure, and now, why should you believe me? Because I have to finish my talk, first of all. Okay? and then. But nevertheless, there are ways. So we have these cross sections. Now neon goes to the blue lines, neon to neon plus, neon double 3 plus, etc. And these now are these direct, that I call neon. 2-photon goes to neon double plus, 3-photon neon 3 plus, etc. It so happens, and the frequency is such. And 690 eV photons take out all 6 2p electrons. And now the red are the direct. Now this is a highly nonlinear system. Now, not only because, for example, to go from neon 4 plus to neon 5 plus, there is a 4th order process here. So this is a banal nonlinearity. It's just the 4th power. But now, suppose you solved these differential equations in some closed form, and you had an expression for N6, neon 6 plus. You see, in there would be all sorts of nonlinearities, right? It would not be just f to the 6. So you would have to take the average over fluctuations of that, and I'm coming to that issue now. So these are differential equations, but they are stochastic differential equations, unfortunately or fortunately, depending on your point of view. Because F, this is the photon flux now that comes out of the source, which is the FEL, and has severe intensity fluctuations. Now, fluctuations of an electromagnetic field say something about its properties, say its correlation functions, something about the source that produced it. So, depending on your point of view, field fluctuations may be a dirt effect, because it doesn't give us, but also it's a very interesting phenomenon because it's a way of studying and understanding field fluctuations in. Okay, so then, okay, I said all of this. Now now how do I get these cross sections? Yeah, it just doesn't, no time. Now, 2 important issues here. We have a pulse here. We have a pulse, and a pulse can be longer, or short. Now, a crucial issue here is that if you want to beat the sequential processes, you want a short pulse. Because if the pulse is long, the sequential processes are of low order. 1 photon, 2 photon, 3 photon, etc. And low order processes, of course, have a high probability at smaller intensity. So if the pulse is long, as the pulse rises, you get the sequential here. And so to be able to see any direct process, including helium, you need a short pulse, as short as possible. And then there is this unpleasant, this is truly unpleasant thing that you have to focus the pulse, to have the intensity you want. So then your highest intensity is at the focus, but then as the intensity rises, the intensity gets high in there. So then you don't collect a signal from a particular intensity, but you collect signal from a volume with different intensities. And this averages things out, but c'est la vie. Now, yesterday, Joachim Ulrich gave you a preview of the structure, but he emphasized basically the bandwidth of the pulse and the temporal structure. Now, to a rough approximation, so far, a free electron laser pulse is a chaotic source. A chaotic source is a well-defined object, a mathematical. It has its correlation function. This has been known. That's why Glauber got the Nobel Prize. It has been known since '63. All its correlation functions are known. It's a field that fluctuates as Gaussian statistics with zero mean and so on. Now, this, however, is not exactly that. It has some peculiarity. So it's pretty close to chaotic. But so now here is a typical. I should say that whatever, since we need to put these fluctuations, George Nikolopoulos has really done a lot of work on this because he comes from quantum optics. So now, so then here are pulses, and here is the average. This is now in time, and in frequency, each pulse has different shape. So what the experiment, in the end, it's what, in theory, as well as in experiment, you have the average over this. So now, n-photon ionization in lowest order perturbation is proportional to nth order intensity correlation function. It's not proportional to the nth power of the intensity. Okay, so that's, for a chaotic source, the nth order correlation function is n factorial times the nth power of the intensity. So chaotic light enhances an n-photon process by factor of n factorial. And if you have a 6-photon process, it's 6 factorial. Now, which is equivalent to increasing the cross-section base. Okay, here is something that I have already said, that these things were studied a lot, field fluctuations. And Steve touched upon that. Field fluctuations were studied in resonance fluorescence, even in multiphoton processes in the 70s and 80s. A lot is known about that. Except that, in those days, even the pulse lasers were long, or in resonance fluorescence they were CW, and all of the work, which is rigorous, excellent work, has been based on stationary and ergodic processes. And two models that have really studied a lot is phase diffusion and chaotic light, as I said. Now we have something that is different. Now we can argue forever about stationarity and ergodicity and so on. It doesn't matter, but we have to take what we know from the machine people. And so here is a sample now. And so we have modeled this. I mean, George has modeled, we have a lot of work done on this. And then Joachim yesterday talked about the coherence time. So roughly speaking, the pulse has spikes, and the shortest and more prominent spike defines the coherence time. Okay? And so, but then you have to decide what the coherence, and then run this. So these are different coherence times. This is now the spectral width. The spectral function can be Gaussian, can be Lorentzian, can be So, and depending on whether you use Lorentzian or Gaussian, the calculation, the Lorentzian is much more demanding. Okay, here is the sample. Okay, now, just an example of what I showed you. I told you. Well, George called it R photon process, N photon process. R is the order of the process, okay? Single photon, 2 photon, 3 photon, 5 photon. This is just one example, just simple example to illustrate the fact. We have a species which undergoes a few photon ionization. And the line is for a deterministic pulse. The points are for a chaotic pulse, chaotic of the type we have in the FEL, which has been modeled on the basis of what we know, okay? Numerical model. And you see now, for this intensity, for 5 photon ionization, a chaotic pulse has much more, gives much more ionization than a deterministic pulse. Much more, huh? Look at that. This is this logarithmic scale, 2 orders of magnitude. It's the 5 factorial. Not exactly 5 factorial, but it's almost 5 factorial. So that's after 50 years of quantum optics, people are still surprised to hear that an incoherent chaotic light is more efficient in doing multi-photon ionization than deterministic light. Okay, now the problem we talked about. So we are going to take all of those cross sections, put them in, and see what happens. All right, and then what is? I have 5 minutes, or 3 minutes. All right. All right. Now, and now here is what we are going to calculate: neon plus, neon double plus, neon up to neon 8 plus, with high order process. Up to neon 6 plus is 6 photon, 6 electron rejection. Just to put some extra things, we put there ionization of the 2s also. So now here is the deterministic pulse, 30 femtoseconds, with or without the direct channels. The dashed lines are without the direct channels. The solid lines are with the direct channels. Now, the pulse short, 5 femtoseconds. 5 femtoseconds, let's look at here. Here now, this is neon 7 plus, this purple line. You see, here is without the direct processes, the direct. Okay, as we expected, the direct process would be visible if you had a very short deterministic pulse. Now, the bad news comes in, that if you have a chaotic pulse of 30 femtoseconds, you still have some enhancement, of course, because of the n factorial, okay? And the direct processes being higher order nonlinearity are more enhanced. Again, you have this. Now, space integration. Space integration, we have taken into account the volume of well, what happens now, instead of the ionic species going up and down, and then the next one coming up, they all now reach a saturation. Now that is a problem. And now there is an experiment. There has been an experiment, and we didn't expect to see much, but here is by Richter, and here, where is neon? Here is neon. Well, this is time of flight. Somehow we had to extract from this populations of the various ions. Okay, here's what we got. Here's the experiment. Neon plus, neon double plus, neon. Here is what we can do from the theory. The solid, the black lines are the sequential only, and the colored lines in which the black are embedded is what we put in for the when we put in the direct. We did not expect to see the effect of the direct here because the pulse was too long. Okay, but what's interesting is that, well, this does not look much different from that. There is a contact with the experiment. So since now the chairman will kick me out, I mean, here is the story. So these direct processes are a universal thing, which should be present. Now, whether they are observable, you can single them out, or whether they participate in the whole soup, it's going to depend on the pulse duration, the fluctuations, and the order of the processes. Okay? Right. Thank you.